Welcome back to Applied Physics. In this video, I want to talk about pressure. Although before I can get there, I have to talk a little bit about force again. If you apply a force to a solid object, that object will deform in some way, shape, or form. Depending on the properties of the material that the object is made of, it might deform more or less. For example, consider sitting on a soft cushion versus sitting on a sturdy wooden chair. The amount it deforms will also depend on how spread out the force is. If you can condense all of the force down to a single point, well, it's not that difficult to drive a nail through a block of wood. And if driving a nail through something isn't deforming it, I don't know what is. On the other hand, if you spread everything out, then that's going to reduce the amount of deformation. This is why some people can train themselves to walk on a bed of nails. If you step on a single nail, it is going to go right through your foot and probably cause some severe damage. But if you step on enough nails at the same time, the force of your step is spread across all of these nails. So the force on one of the nails trying to drive into your foot is relatively less. And if you have enough nails, you can take that force down to the point that it can't break your skin anymore. Mathematically, we describe this sort of behavior as stress. The formula for stress, we'll use a capital S to represent the stress, and it's simply the force divided by the area. In the SI units, the unit of stress is the pascal. I think this is the first unit we've come across where we use two letters to represent the unit, but capital P lowercase a is a pascal. Force is measured in newtons. Area probably makes the most sense to measure it in square meters, so 1 pascal is 1 newton divided by 1 square meter. In the US customary system, it is much more common to measure stress in pounds per square inch, PSI. I don't even know if this counts as a definition, but pounds per square inch, take pounds, divide by square inches. Now, pounds and newtons are relatively similar sized units of force. 1 pound of force is about the same as, I think, 5 newtons of force, somewhere thereabouts. That's not a conversion that I know off the top of my head, but I think it's close to that. But in the denominators, square meters and square inches are drastically different, right? A meter is actually so long that I can't hold my hands that far apart and still fit them on the camera. But a square meter takes up probably a little bit more space than the writing surface that you are working on right now. A square inch, by contrast, about that by that. A meter is close to a yard, and a yard is 36 inches. Let's round that up to 40. So a square 40 inches by 40 inches would be 1,600 square inches in a square meter. Right? So we're dividing by something 1,600 times bigger up here than down here, which means that a pascal is a much smaller amount of force than a PSI. Where's the number? There it is. 1 PSI, this is the one that I actually do have on hand. 1 PSI is 6,890 pascals. And I think with that, it also becomes kind of apparent that the pascal isn't usually going to be the unit we want when we're talking about a stress. Instead, it will be a lot more useful to us to talk about kilopascals, thousands of pascals. And at that point, the units become a lot more reasonably similar in size. As a quick example, let's consider a rectangular block of some material. And let's say that this block measures 1 inch by 2 inches by 3 inches. And let's further say that it has a weight of 2 pounds. As I drew it, it's kind of just floating off into space, but you can think of it as sitting on a table or some other sort of a surface. And I just realized that I labeled it backwards because I wanted it drawn so that the 1 inch was sticking up and the 2 inches by 3 inches were the part that was resting on whatever surface it is resting on. Well, then the area, as far as stress is concerned, is the area of that rectangle down there, which measures 2 inches by 3 inches, or is 6 square inches. And then the stress is going to be the force divided by the area, and weight is a force. It is the force of gravity. So we actually have that number. The force is 2 pounds. The area is 6 square inches. And that comes out at 0.33 psi. If you take that same block and you turn it on its side, so instead of the 2 inch by 3 inch part being on the ground, let's rotate that so that the 3 inch part is the part that is standing up. And then the area that is on the ground, in this case, is the 1 inch by 2 inch face. So that's an area of 2.0 square inches. And the pressure, or the stress in this particular case, is 1 psi. Right, so stress is a property of a material. It's actually a property of the interactions between two materials. So it doesn't depend just on what kind of thing is causing the stress. It doesn't matter just what the force is. The orientation is also important. Moving onward, we said we were going to talk about pressure in this video, so let's do that next. Pressure is a source of constant stress. This sounds like mental health advice, but the vocabulary is surprisingly similar in physics. There are a number of different ways that you can apply a pressure. Right? Going back to that example of the block. If you just take that block and set it on the surface and leave it there, it is now pressure because it's constant, it stays the same. Compare that to if you are walking across something. Well, you're going to take a footstep, you're going to apply some stress, and then you're going to lift your foot and put it down somewhere else. The pressure is changing, or the stress is changing, so it is not really pressure. That doesn't quite make sense. Standing still, I guess you could say that my feet are causing pressure because I'm staying in one place. There's a lot of nuance there, most of which we aren't going to worry that much about, but we will use it as a reason that we can talk specifically about a kind of pressure hydrostatic pressure is the pressure, the stress of being in a fluid. So let's see how well I can draw this. Let's consider a cylindrical tank. And this cylindrical tank is filled to some level with water or some other liquid. I don't really care what it is. The properties of the tank, well, we can talk about the height of the tank, but it turns out that's not really all that interesting, because instead, what is interesting is the height of the fluid within the tank. And then the tank has some sort of a shape. I said that this was cylindrical, so in my particular picture, this is going to be a circle. We can calculate the area of a circle given information about it. But let's just stick with there is some area. If you have a surface of a given area, and then you fill up some height above it, well, you can calculate the volume as the area times the height. When we're talking about fluids, we also might be interested in talking about the density, right? So depending on what kind of fluid it is, density is mass divided by volume. Rearranging that equation, we can write that mass is density times volume, and then substituting in, since volume is area times height, the mass is the density times the area times the height. So, if we know the density of the fluid, and we know how deep the fluid is in the container, and we know the area of the surface of the container, we can calculate the mass. And so let's consider something that is right at the bottom for now. If we were talking about something that was further up, we just have to change where our height measure is, but let's think about something that is right on the bottom of the container so that all of this fluid is above it. And to calculate the stress, well, we need force divided by area. Force, I guess it'll be the gravitational force. So I should have put that up here somewhere. Fg is m times g. So we have mass times gravity divided by area. And mass is, of course, density times area times height. And the areas cancel each other out. And yes, this was a stress, but we specifically said that this was hydrostatic pressure. So let's go ahead and call it P instead. The hydrostatic pressure acting on an object is equal to D times H times G. where d is the density of the fluid, h is the depth of fluid, or the depth of the object in the fluid, and g is our gravitational constant, as long as we are on the surface of the Earth, 9.8 meters per square second. The area doesn't matter, and that's incredibly useful to us in this formula, because now we don't have to worry about, well, the pressure on the entire bottom plate. If we have an object that is just taking up a small amount of space, well, only the fluid that is directly above that object is applying pressure to that object. The rest of the fluid is applying pressure elsewhere in the container. So it's nice that that all cancels out, and we just have to worry about the depth of that particular object. That also means that we can move the object, right? We can talk about the pressure on an object near the surface, a little bit further down, a little bit further down. If you happen to have or have had in the past a water-resistant watch, water-resistant watches are always rated at some depth. I happen to have one that is rated at 50 meters. So if you have the watch down up to 50 meters of depth, it works perfectly fine. Below that, the water pressure becomes significant enough that it can overcome the waterproofing that was made in the device in the first place. So let's consider as an example here a relatively tall cylinder. And we'll fill that cylinder up near the top height. And then the interesting thing we're going to do is we're going to drill 3 holes into the side of the cylinder. And from each of those holes, the fluid will flow out, and the rate at which it flows out is going to change depending on the pressure at that point. So we need to know a couple of pieces of information. Let's say that each hole has a diameter of 0.4 centimeters. We have the holes 10 centimeters apart, and we filled up the water so that the level here from the water to the first hole is 10 centimeters, from the water to the second hole is 20 centimeters, and from the water level to the bottom hole is 30 centimeters. I also did say here that it is water. Knowing that it is water is incredibly useful because the density of water is 1 gram per milliliter. That's actually the definition of the gram. The density of water is 1 gram per milliliter, and 1 milliliter is 1 cubic centimeter. And I think leaving things in grams might actually be perfectly fine in this case. Maybe not. Let's change that to kilograms. I do think I'm going to leave things in cubic centimeters instead of trying to convert things into meters, because we have centimeters here, we have centimeters up there, and everything is working out perfectly fine. Right, but our pressure, we just figured out, is the density times the height times gravitational acceleration. And the units here are going to be really stupid at first, but things are going to work out more or less okay. Are they? No, oh no, I'm wrong, they're not. This is going to be a lot easier. If everything is in kilograms and meters instead. Right, so take our density, take our height. I'm just going to do the first one because once you see the calculation, you can do the others on your own. Right, so we'll have kilograms, meters squared divided by kilograms, meters per second squared. That's our newtons. And then we have cubic meters and meters, which is going to give us newtons per square meter. That's going to be our units of pascals, which is what we usually use. And the math here is fairly straightforward otherwise. 980 pascals. Now, one thing that I didn't do in this calculation, I gave us this other number up here. Each hole is at a depth, or has a diameter of 0.4 centimeters, 0.004 meters. I can calculate that the area there is pi times the radius, which is half the diameter, 0.002 meters squared. Which is an incredibly small number, 0.000013 square meters. But the interesting thing here is now that we know the pressure and we know the area of the hole that it's going to be going through, well, if stress or pressure is force divided by area, then force is pressure times area. If I take that 980 pascals and I multiply it by the 0.000013 square meters, I get that the water that is escaping from that top hole is being pushed out with a force of 0.012, and pascals is newtons per square meter. Multiply that by square meters, we have newtons. For the sake of time, I'm not going to go through and look at the other two holes, but I think it is interesting to try to go through those one by one and see how changing the depth changes the amount of force that the water is pushed out at. You can then use that force to figure out the acceleration. You can use that acceleration to figure out how far across it is going to go before it lands on wherever the container is resting on. And it's an interesting balancing point between the higher the hole is, the further the water is able to go before it hits the ground, and the lower the hole is, the more force it has, the higher the acceleration it has in the first place. Right, that's a little bit beyond the scope of the course, but it's an interesting thing to think about, so I wanted to at least get that far before we moved on. I do have one last topic for this video. And that is air pressure. The air in the atmosphere is a fluid. A fluid is any liquid or gas, anything that can move around objects that try to pass through it, anything that can reform itself to take the shape of the container it is in. And because air is a fluid, that means that the air is causing stress. You are under pressure from the atmosphere. Very often, to make life easy, we defined a unit. The atmosphere, ATM, is the amount of pressure that is caused by being on the surface of Earth underneath the atmosphere. One atmosphere is approximately 1.01 times 10 to the 5th pascals. And I'll also mention that that's on the ballpark of 15 psi. This fact causes a number of different concerns and headaches. First of all, it causes literal headaches. There are a lot of people who suffer chronic migraines that are triggered based on fluctuations in the air pressure of where they are. But on a more practical sense, it's going to cause issues with how we measure pressure. It turns out that we're going to need to take into account, whenever we are measuring a pressure, whether we are measuring what is called sometimes a relative pressure, but in industry more often a gauge pressure, or an absolute pressure. The difference between these is that a gauge pressure is 0 at atmosphere. Right? If you are thinking about a helium tank, if the tank is empty and there's no seals on it whatsoever, and you look at the pressure indicator on it, the pressure will read as 0, because the pressure is the same as atmospheric pressure, relatively speaking, no more pressure. Once you seal everything up and you start pumping air in, helium probably, that's going to cause the pressure in the tank to increase. So the gauge will read how much the pressure has increased compared to the outside pressure. And in a lot of ways, that's actually incredibly useful. Right? If you have pressure outside of a vessel pushing inward and pressure inside of a vessel pushing outward, in a lot of ways, those pressures cancel each other out. Right? So if you have pressure that is pushing out, and you have pressure that is pushing in, the question is not how much pressure is there. The question is how much difference in pressure is there. If the difference in pressure is too great, it will cause the container to warp. If the internal pressure is higher than the outside pressure, and it exceeds the amount that the container can handle, the container will rupture and possibly even explode. If the pressure inside is too small, it will cause the container to rupture, to implode on itself. And either way, failure of the container depends on the difference between the outside and inside pressure, which is why a relative pressure or a gauge pressure is very often useful in industry. But not always. There are times when the absolute pressure is more important. We'll talk more about some of those a little bit later in the course, but for right now, it's a fairly simple calculation. If your gauge pressure is reading 27 psi, and you know that the atmospheric pressure is 15 psi, well, you just take the absolute pressure as the gauge pressure plus the atmospheric pressure. What did I say? 27 psi plus the 15 psi that I said was approximately our air pressure. Add those two numbers together, and you're going to end up with 42 psi is the absolute pressure of whatever is in that container. With that, I think I have talked long enough, so I'll wrap up the video here. Thanks as always for joining me, and I'll see you next time.